Hey, welcome everyone to the Buckeye State Chapter webinar on fiber to the home, passes to the premise. Here in a few minutes, I'm going to introduce our guest speaker for today. Attendance is really good, and I just wanted to remind everyone that with this webinar, you can't really voice your questions, but at your site or at your desk, you have the panel and you can type a question. I'm going to be following those questions and when appropriate, getting Chris to speak to those. And just a little bit more housekeeping. For sites that are dialing into the webinar, I'd really like to have you fill out the attendance sheet. If you don't have one, send me an email at some point after the presentation. I'll get you the attendance sheet. It's the same one we've used in the past. Fill it out and then return it back to me. I'll be responsible for going through LMS, making sure everyone gets credit. And then lastly, we are recording the session today. And for those of you who didn't know, we have updated the SCTE Buckeye Chapter website. An email went out a couple of weeks ago that had the links to the new website, and I think you'll enjoy the new style. And as we expand our reach to include hyperlinks to some of the recorded sites, I think you'll be able to go back and even replay the content and learn some more. And in a couple minutes, I'll read Chris's bio and we'll get started. Again, folks, welcome to the Buckeye State Chapter training for fiber to the home. I want to introduce our guest speaker. He's Chris Bright. He's the Senior Field Applications Engineer for CommScope, specifically the CommScope Connectivity Solutions. Chris has been around in the industry for a while. He joined in the early 80s. As I said, he's the Senior Field Applications Engineer. He's had experience in both broadcast and cable TV markets. His current duties at CommScope include providing both pre- and post-sales field engineering support and guidance for CommScope's MSO customers. He's currently involved in several product development and projects related to the fiber to the home networks that customers are deploying nationwide. In order to support all this activity, he's spending a fair amount of his time at work sitting in pressurized aluminum tubes, 30,000 feet in the air, going 500 miles per hour. So his frequent flyer miles are adding up. Throughout his career, he's been involved in many aspects of RF, microwave, and optical communications, including satellite uplinks, remote sports broadcast operations at Bonneville Telecom. He also spent 6 years as a senior head-end microwave engineer at Cox Communications out in San Diego. He's a member of the Fiber to the Home Council, the SCTE, and as an SBE certified broadcast engineer. If you all are amateur radio folks, you can catch him. He holds an FCC Class A certification and is an FCC licensed amateur radio operator. His call letters are KC6VEG. So Chris, welcome to Ohio, and take it away. Thanks.
Great. Thanks a lot, Bill. I appreciate the introduction. I think I can guess by all the things you just stated about me, the only one thing I can say for sure is I must be fairly old. So time passed under the bridge, as you well imagine. But thanks very much, Bill, and to the Buckeye State Chapter for inviting CommScope to present today. Today I'll be discussing fiber to the home from what we really refer to as the layer one physical connectivity perspective. That is all the physical devices, the cables, splice closures, cabinets, hubs, terminals, things of that nature, used to support any fiber to the home type of network that's being built or designed or deployed, whether it's a single family unit or a multi-dwelling unit. Certainly both of those types of design criteria would apply. And we're going to also discuss today basic design architectures, such as centralized architecture, a distributed architecture, and a tapped architecture. What that really goes to is where are we placing the optical splitters in the network, okay? And based on the type of serving area, that may change. So we'll also look at the types of equipment needed in the outside plan used to support both single-family unit, also known as SDU, and MDU, or multi-dwelling unit residences. And as Bill mentioned before, once we conclude, I'll be happy to field any questions you folks might have. So with that, I'll get going here, and we'll dig in. So when we talk about architectures or fiber to the home architectures, it's important to note that there's certain things that drive that decision. Certainly the housing type and density of the homes is going to determine the architecture type. That's probably the most important thing. You don't want to spend more money building a network that's overbuilt to support a small serving area, obviously. So closer to the city center is going to yield more homes passed. That kind of drives itself towards a centralized type of architecture. Distributed, further out from the center of the city, less homes passed. You can see I've used my home state here of Minnesota as an example, since I'm mostly familiar with the city and its surrounding areas, and I've highlighted those as going from the outside in as low density. Anything in green would probably be served best by a distributed type of architecture. Because we have less homes per passed, we don't want to put all this equipment out in the plant that's just not going to be used or is too dense to support the sparse homes passed per mile, if you will. Then you move a little bit closer in and you get into the urban areas where it's going to be red red and or blue for the high density urban. So medium density, you might think of distributed or centralized. Once you get to a high density urban area, centralized tends to be the most efficient type of architecture to use. So what I wanted to talk about briefly, we'll touch on each of these, are the types of architectures related to where the splitters are located in the network. And I mentioned that before. With a centralized type of design, all the optical splitters are housed in one location. In this case, they would be called fiber distribution hubs, fiber distribution cabinets, whatever. It's a protected, environmentally hardened device that sits in the outside plant, probably on a vault or a pedestal where the optical splitters are located. From that point, all of the customers would have their drop cables essentially run from that centralized point right to their homes through several devices in the network, of course, which we'll talk about. But then we look at distributed splitters. This is where we're going to put an optical splitter further back, whether it's in the head end or in a distribution cabinet out in the field, and then at the optical taps or naps, several different names to call them, we would place another optical splitter. And it's generally in the cable industry, we're using fiber to the home right now, transporting a RFOG spectrum out there. So it's typical that we use 1x4 and 1x8 splitters in a distributed architecture to yield us that 1x32 split, which equates back down to about a 17 dB loss, and that fits into the network design criteria with regard to optical loss into the system. So that's distributed, and then we can look a little bit further for much more sparsely populated areas as a tapped architecture, where we're not using optical splitters now, we're using optical taps or uneven port splitters, much like we do in a traditional coax distribution network. And then that gets us much further out into more rural areas, spending less equipment or capital cost to push that equipment further out into the network. So, and I did mention cost there, so of course economics always plays a part in determining what type of architecture to use, and just a couple of generalized bullet points here. Centralized and distributed splitter techniques and architectures will often be cost effective for medium and high subscriber densities, as I mentioned on a couple of the slides previous to this with the urban and suburban serving areas. Tap architectures are going to offer you significantly lower material costs and better fiber use when you get into those medium and low density installations, when you get out into the rural areas of where your network is located.
Chris, a question.
Yeah.
So traditionally in those urban or suburban taps for the coaxial drops are essentially every other lot line, poles or pedestals, and so drops are relatively short in the scheme of things and don't generally cross over someone else's lots.
Correct.
Will you speak to that? Do you have a slide forward that speaks to what kind of challenges we might have with drop lengths in the fiber world?
I'm not sure that I have a slide that directly addresses that, but your statement is correct. And I guess what I could say is that in general, when these networks are designed, they're using the same type of tap port quantities, 2-port, 4-port, whatever makes most sense in covering that serving area.
Okay. Thanks.
Okay. Yep. Okay, so we'll jump ahead here and look at our centralized type of architecture. Again, this is very straightforward, and the other two types of architecture, distributed or tapped, are just a deviation off of this type of architecture. So just again to show everybody where the equipment is placed in a generic network, I'll call it, starting off from number one, this is what we would call a fiber distribution hub or a cabinet. This is the central location for the splitter. All homes that are going to be served off of this cabinet are indirectly going to have a a fiber cable run directly from that hub to their residence. That's going to consist of the fiber distribution hub, the splitters, and the vault that it sits on in spot number 1 there. Then we move further out into the network where we have the splice cases, okay? So this is the distribution side of the hub, and we're going to make our splices of our devices, which we refer to as here multi-port service terminals at position 3 in this drawing. Now those guys can be mounted either in a pedestal, a handhole, or on an aerial mount. It's also referred to as a NAP. I've heard them called several different things. MSTs, which is multi-port service terminal, NAP, network access point. I've heard them referred to as fiber taps. They're all, fiber taps not 100% correct because it is a home run from the hub out to the customer, but you get the point. People go with what they're familiar with. So saying a tap tends to make sense at the fiber cable plant, even though it's not 100% correct description. Okay, so that's position number 3, and those are the devices, Bill, I was talking about. They're typically, there are other values, but most typically used are 2-port and 4-port. Okay, and then we get to the drop cable, of course. This can be overhead or underground. You should be looking for cables that support both types. If it's underground, you might want to have a tonable cable. If it's overhead, dielectric's probably going to be fine. Okay. Okay, so I just wanted to spend a little bit of time on each one of those types of architectures. We have our centralized splitting architecture. And just some broad statements here about that is that it's the most popular type of architecture. It was really the first one out there. It's well known and offered everywhere. The architecture is taught at different types of PON or RFOG training and design courses, and it's real comparable to the legacy copper telco networks in the way that it's laid out. The material costs obviously are higher than the tapped architecture until our densities get up to that suburban and urban range, anywhere between 170 to 350 homes passed per mile. So obviously it's good for high density inside building and MDU types of applications, but for low density, for more rural applications, centralized splitting architecture is not what you would want to employ. Then we look at a distributed splitter architecture. This is just a variant of centralized. Again, the first splitter can be located in the head end or the fiber distribution hub or cabinet, whatever you want to call it. So as an example, we would put a 1x4 or a 1x8 splitter in there if we're dealing with an RFOG network. The second splitter is going to be located out in the tap location, as you can see in the drawing to the right. And that would be the complement. If it's a 1x4 back in the fiber distribution hub, then we're going to have 1x8s out in the field. In this example, we could have a 1x16 splitter in the head end and then 1x2s at each one of those tap locations. The combination of those two splitters together is going to give us our 1x32 split, or our 17 dB optical loss in the transport network. Okay. One of the advantages of this is that it's the least fiber length of all, drop fiber length of all the alternatives. There's less material costs in a centralized architecture. We are going to potentially have more taps because we're going to have more installation locations, and it's good for medium to low density.
So with more taps, more optical passive loss, correct?
Well, they'll all be equal. As an example, like I said, if there's more taps, there will be. These aren't, and I should probably back up a little bit. These do say T, which would indicate tap. It's actually a splitter. So I apologize for that. Somebody else's drawing I stole. So
with potentially different optical losses, trying to balance what gets to the customer.
Well, no, that's in the tapped architecture. Like I said, this is distributed, where we're using splitters at the fiber distribution hub back at the origination point, and then we're using equal loss leg splitters in the field. In this example, this would be I believe a 1x16 splitter in the head end, and then a 1x2s out in the field.
Okay.
Okay. So then we'll talk about tapped architecture. I think that's what you're referring to, Bill. In this case, best for rural applications, 25 homes passed per mile. And typically all you're going to do here is you're going to have, excuse me, distributed pond type cabinet out in the field where we're going to place one type of splitter. And then the tap is going to be out in the field closer. We're going to cut one of the fiber cables. In this case, it's showing a 1x4, but in reality, in my picture down to the bottom, this is going to be a unequal value, like a 14 or 11 or 9 dB loss. A couple other advantages, like I said, is it reduces the fiber counts again, just like the distributed did. And fiber distribution cabinet can be used, but it's not really required. It could be a splice case could suffice with the optical splitters in there. Okay, so what I'd like to do now is we've talked a little bit about architectures, whether it's centralized, distributed, or tapped architecture, just to give you a flavor for that part of the equation that is going to determine how the network's designed. Now we're going to look at examples of those designs put into play. And at least for today's discussion, I've kept it to the centralized because we just don't have that type of time allocated to go through every type of architecture for both single family unit and MDU. So I hope that's okay. And I just want to identify the devices out in the field, where you can expect to see them, perhaps what these maps are going to look like, what is straightforward. These admittedly are pretty straightforward, simple designs, but they're good to look at and get an understanding of them. I'm sure that with our audience today that there are people with different levels of understanding and knowledge of fiber to the home. So certainly this presentation isn't going to get into the deep down dirty details, but at least it might help to level set everybody's background and understanding of where these devices fit within the network and how they all play together. So this is the first one I wanted to show you. It's just an example of a greenfield application. In more cases than not, when fiber to the home is deployed, it's almost always at a greenfield application, because doing an overbuild on the existing network, to be honest, doesn't really make financial sense, at least not for the near term. So most of the projects I've been involved in have almost been universally greenfields or new builds. They're typically a phased development, not always, but a lot of times there are, where they'll build up 40 to 50 to 100 or 200 or 300 homes in a large plan unit development or something of that nature. Because it's new, it's almost always universally going to be underground construction. Sometimes the contractors can get a little bit of a financial benefit if they do joint trenching with the utilities that are being put into this development at the same time. That's another, quite a large advantage versus a brownfield in our existing plant. And then, as I mentioned before, phase one, a lot of these are designed and built in phases. So the complete thing won't be built at once, but when you do the design for it, you need to plan ahead with regard to your feeding fiber coming into the into the project, that it's going to have enough fibers to serve the whole area. So you must think quite a ways ahead when you're dealing with planned phase development of these greenfield fiber to the home builds. And as always, at least for the MSO market and for cable operators, RFOG is kind of the standard that we've been shipping out there today, but we have to plan ahead for Ethernet PON or gigabit Ethernet PON in the future. And certainly all of these devices support that. The only thing that's going to change is the transport equipment, and back in the head end will turn into what we call an OLT, and then out in the field at the customer premise is going to be an ONT, and those will be the two devices that essentially trade information back and forth in IP packets versus any type of RF medium going out there, or RF based optical signal going out there. Okay, and here just wanted to drill down a little bit further. In fact, I'm going to back up one slide. Oh, sorry, I'm going to go ahead. This is one, I just turned it sideways, and I just wanted to show you and help you identify where all these devices are. Hopefully everybody can see my laser pointer down in the lower center of the slide. This is the fiber distribution cabinet. This is where the fibers come from, either a V-hub or the head end itself into this cabinet in a centralized architecture. This is where all the optical splitters are going to be placed, okay? So now we have two legs going off of that fiber distribution cabinet, one heading to the left in vertical, and then out of the cabinet and heading up and to the right to serve the right-hand side of the serving area. Now, I'll point out a few other things here going from the bottom to the top. The distribution fibers to the MSTs, or the taps, I'm sorry, not taps, I won't call them taps, are in red. Hopefully everybody can see those lines. The drop cables themselves are in blue. As you can see in this design, they're using 1x4s. Okay, so that works out pretty well in this type of serving area. Further to that, you're going to see the MST splice closures, and they're usually fairly simple to identify with a drawing like this, because if you see the green tails, those are the cables coming from each of the respective MSTs. And as you can imagine, in this block up here, we have 1, 2, 3, 4, 5, 6. So we're going to end up with 6 cables down in the conduits towards the splice closure back at the street here. So they tend to build up. Okay, so that's where a lot of the equipment is located in a residential single-family development. Drill down here just a little bit further. As you can see, I've turned the slide sideways again. We have our hub, our 2 feeding legs, which are in red. Okay, then there is a hand hole right here with an MST splice case located in it. And then if we drive up this street here, we're going to see all those MST tails that are in green going up and then stopping at 1 location, 2 locations. Okay, and then the drop cables, of course, are in blue. So that's a typical centralized design. I want to look at the actual equipment here and give you a flavor for what that type of stuff looks like. Certainly I'm using slides from our company. There are other devices out there, but they essentially do the role of protecting and managing that optical splitter out in the network. Okay, so for most of these types of uses, you're going to look for a sealed enclosure. It protects the fiber from dust and water, other contaminants in the outside plant, obviously. It should have pre-termination configurations. The most common configurations are 72, 144, 288, or 432. And what that number refers to is the number of fiber cables, individual fibers, on the distribution side of the cabinet. Okay? So the cable routes for all the bend radius and strain relief should be easily identifiable. You can see that in the pictures, how well they're managed. Another key thing to have is a swing frame, so you can swing out that and gain access to the optical connections in the back if need be. Chances are the only thing you're ever going to do in this device is install optical splitters to enhance the capacity of the cabinet as the serving area or the development grows. Okay.
Larry, all passive, correct?
Correct. There is no active devices in the outside plant, most typically with fiber to the home, with the exception of the V-hub or the optical node that's going to feed this cabinet. Okay, so from the fiber distribution cabinet or hub to the customer, 100% passive. Okay, these cabinets, of course, should be pad pull or rack mountable, and at least with the CommScope version, we use what's called a plug-and-play splitter. So it simply snaps into position, and then it has 16 or 32 pigtails that come out of it and route around to the front and then plug into the subscriber access panel. I'll show you that on the next slide here. So up at the top, this is where the optical splitters can mount. Don't know how good your picture is on here, but if you can see in the rear, this is the 1 fiber cable coming from the head end where my laser pointer is. So that's the feeding fiber of the splitter. Then this device where you can't see it, but there's 32 2-meter pigtails that route out down, and then up through the cable management and into the subscriber access panel. At this SC angled bulkhead panel, every one of those ports on the bulkhead panel is basically connected directly to a customer out in the field. Okay, and then any unused outputs from an optical splitter that's located up on the top can be set down below what we call a parking lot. And all that does is keep the fiber connector protected and clean while it's not in use. Optical splitters, this is what one of those devices looks like. It has a single fiber input, and then it has X number of outputs on it. In these picture examples, the lower picture is a 1x32. Okay, so we have one fiber coming into it, 32 fibers coming out. The picture up on top here, this is a CWDM or a DWDM device, which is used a lot of times to drive directed, dedicated services to businesses that may be in the same general vicinity that your fiber to the home development is in. Okay. Their pigtailed outputs, like I said, anywhere from 1x2 up to 1x64 that they're available with as far as split ratios. There we go. Here's the schematic of a fiber distribution hub. Like I mentioned before, it's a completely 100% passive cabinet. There is no means for powering it. There's no need to power it. If we look at the signal flow from the left-hand side, we're going to have our cable coming, whether it's from a node, directly from the head end, a V-hub, whatever the device is that's giving us that optical signal that we're going to use, is going to feed into the cabinet. On the feeding side, it's possible that this would be spliced in. It's also possible that the cabinet itself would have long pigtails or long outside plant cables that would integrate or splice into the existing outside plant. So that fiber cable coming in, if we just use one of those fibers as an example, will come into the optical splitter. We're going to split it 32 ways, and then the outputs are going to go drive and be plugged into that subscriber access panel here. Okay, so as I mentioned before, some of the common counts. If it was a 144 cabinet, I would have 144 SC angle bulkheads here to support 144 homes on the distribution side. Any other patch cords or pigtails that are unused go sit down in the parking lot until the neighborhood grows or another customer comes on. Then you would go rescue one of those fiber pigtails from the parking lot, go identify the customer on the subscriber access panel, obviously clean both connectors, plug them in, and you've just activated service to that customer. The output on the distribution side could optionally go through a splice tray or have a pigtail that would integrate into the existing outside plant. So we look at the cabinet itself. How does it mount into the outside plant? This is, of course, the ground mount version. It sits on a riser pedestal, usually about 6 inches or so. It's a ground spacer, you could also call it. And then it sits on top of what they call a fiberglass mounting sleeve, or a FDH vault. Within this vault, this one is 47 by 68. So this is a rather large one, at least in my experience. Don't usually like to use them that big if we don't have to, because then that requires a backhoe to come out and dig the hole. With smaller vaults that are like 30 by 60, you can hand dig those. It's not fun, but you can hand dig them. It's not too tough of a task. Now, when we talk about both the feeder and distribution cables on the cabinet itself, as you can see coming in here, those are going to need to be spliced into the network. We're going to have a feeding side that's coming from the V-hub or the signal origination source, and then we're going to have a distribution side that's going to go out and feed all of our customers. So when you install these, you just plan on there's going to probably be at least 2 splice cases down underneath the fiber distribution cabinet. And if you recall in the slide at the very beginning, we're going to have a lot of splice closures out there, typical sizes that are nice to support a fiber to the home build, or and you're terminating anywhere from 96 to 144 fibers. Until you get back to the fiber distribution cabinet, then you may need larger scale splice closures that are, upwards of 500 or so fiber splice capacity. This is always going to act as a splicing point for the fiber distribution hub to the NAPs or the MSTs, those tails that come off of those devices. And I'll show you what those look like here in a couple of minutes. The splice closure always needs to be able to be mounted in underground or an aerial application. Obviously, the most important thing is for that thing to seal against outside influences in the outside environment. So it has to have a really good seal on it, so it's not going to leak water or any type of allow any type of contamination into the device. Another thing that makes it really user-friendly is if you choose a product that allows you to re-enter that splice closure easily without cutting off, shrink boot and bishop's tape and all of that stuff. Select a fiber closure that's easy to access again, because you may need to get in there again to add to the network. Also, you should be prepared to use drop cable distribution cable repair kits, is this picture in the middle here in the lower bottom. Nothing can protect against properly motivated landscape project that went out of control, and you've got a customer that has dug up his drop cable. So always be prepared to have something like that on board. Okay, so this is what I was referring to as the network access point, more commonly referred to as a multi-port service terminal. The most common versions of these are the 2, 4, 6, 8, and 12 port in what I call the 2x N style. That means 2 rows of hardened connectors by N number of connectors, 2, 4, 6, 8, and 12. There is a 4x3 version. This is a lot less commonly used. It requires a pretty big footprint to mount it in, when you can get away with the 2x N version. So, like I said before, this device is referred to as a lot of things, but if you think about it from if you relate a traditional cable coax plant, we call them taps or DTs, directional taps, whatever. So people do refer to these as fiber taps, but in reality, remember, it's not a tap in these guys, at least with a centralized architecture. These are all direct run cables right back to that fiber distribution hub and one of those optical splitter outputs. Okay, so again, referred to as an MST, a NAP, fiber tap, etc.
Larry, the MST, is that a standalone device, meaning that you'll need a fiber optics splicer to tie it into the cable, or is that a connectorized device and you put a connector on the end of the cable that comes to it and you plug it in?
That's a really good question. These devices use what we call hardened connectors. Okay, and there are devices out there that act in the same capacity as this, acting as a point to grab that signal to run it to the drop, but they are spliced. So there are any number of different types of devices that could be technically called an MST or a NAP, whether they're spliced or use hardened connectors. That's up to the individual customer how they want to design and build their network. I think personally having the hardened connector there is the wisest. It's the quickest to install, doesn't require fusion splicing out in the field. It's most commonly associated with the typical what I'll call SOP, or just standard operating procedures for a drop cable connection to a house, regardless of whether it's optical or electrical. Okay. So I guess bottom line, if I jump back to this one, depending on what your company decides to use, it may, and it probably most commonly will look like this, but it also may be more of a box-like device with the drop cables just coming out the bottom, and you won't have any hardened connectivity or any hardened connectors on the front. It'll simply be, the drop cable will simply be a fusion splice inside this device that's going to fit up on the strand or in pedestal.
So Larry, the questions come up, and I think they're kind of anticipating it, but since we're talking about the cable that goes from your MST back to your main cabinet, it may go to a splice case. What about sparing? What happens in terms of sparing? Obviously, on the coax side, there isn't any spare coax or spare drop, so if something gets cut, it's got to be fixed. But what about in this particular case? Are there cables that are slightly larger, and if something goes bad with one cable, you can swap it over to another? What's your sense of that?
Not to my knowledge, you know, with every MST, and again, I'll point you to my laser pointer here, this area coming off of where I'm pointing to in the bottom of the MST, we refer to that as the tail. Okay, so that's got, in this case, it would have 4 fibers in it. In the case of the 12 port, there's going to be 12 fibers in this. It looks like it's a flat drop cable design, so it kind of looks like a flat drop drop cable, but it would have 12 fibers in it. With regard to sparing, you know, I don't see any other way around it. If this thing gets dug up, it's probably going to have to be replaced. So whatever spare capacity and length you think you may need of MSTs to keep in the warehouse in the event of this happening, that would be up to the individual customer. But certainly I would go with longer lengths, you know, in the 500 to, most of these are, you know, 200, 300, 500 foot.
Okay, so it ends up being 1 fiber per home, tied all the way back to the splitter network inside the cabinet, and tends to be catastrophic in terms of dig up. So you've got to fix that to restore service.
Yes. Now I will add one little other scenario to that that's much more common, and that is a technician accessing this MST and trying to plug a hardened drop connector into it that hasn't been trained, and he has somehow unintentionally damaged the optical connector inside the device. In this case, it's not as bad because, you know, it's not like a dig up where all 12, in this example, if we use this tap here, all 12 customers were knocked off of service. We'd only have one customer where the installer damaged the connector. Now with the CommScope MSTs, at least, you're able to open these guys up and access them and effect a field repair inside them on that connector. Okay, so in that event, that's a much less catastrophic thing happening to the MST versus a total dig up. But yeah, if it's dug up, there's probably going to only be one alternative, and that's to repull a new MST of the same port value. Does that make sense?
Sure does.
Okay. Just a slide here on how MSTs are typically mounted, at least in pedestal and below grade. Just a couple of examples here. It's a typical 12-inch square ped, 8-inch round. They'll fit in just fine. Any type of vault with an arm mount is obviously much better. As I said, these are environmentally hardened. So if this MST is just sitting in the vault, that's fine. You know, as long as the hardened connectors were installed correctly and tightened down correctly, it's not going to leak. Even if it's, you know, under 3 or 4 feet of water, it's going to be fine. But better make sure that that all those ports are closed off and correctly tightened and closed off. If we look at another type of, I'll hazard to call it an MST, but it pulls off the same job that an MST does, but only for like a garden style type apartment where they might all be ground level, you know, 2 or 4 home duplexes or quad buildings. This is a good type of device to use, and it's called a terminal. So we're going to have no splitters occupying this device. That's back at the hub, but we may have, you know, 6, 12, 24, 48 fibers being sent from the fiber distribution cabinet out to this device. Now we have to be able to terminate the fibers and manage those drop cables into this device, which is going to be mounted on the side of the wall. This is typically used in a indoor drop cable environment, which most greenfields, again, are going to give you that advantage of having microduct or some sort of conduit, or being able to pull the cable into the residences before the walls are put up. Okay, so you probably going to have no issues running indoor cable. If it's brownfield, now the whole building's closed up. Now we have to run all the drop cables exterior to the building and the residences, and then go underground or fix it to the side of the building. But then in all cases, you have to plunge a hole through the side of the wall to run the cable into the inside. So, you know, of course, there would be a NID box or something like that to place the RFOG micronode in that little NID box as well, but you're going to have to blow a hole through the side of their customer's house in a brownfield environment to get that drop cable in. Okay, so like I said, in these, the most common sizes of these are 6, 12, 24, 48, and 96. Rarely would you use a 96. The most common ones are probably 12s, 6 and 12. Let's look at the hardened drop cable that we're going to use coming out of one of those MSTs. I just wanted to describe this cable briefly. You know, the standard outside of it is a hardened flat drop. It looks just almost like flat drop telephone cable. It's about the same dimensions or so. It's very rugged and robust and protects the inside fiber cable from harsh outdoor temperatures and conditions. Second thing we want to look at is the interior of it. In most cases, these, if you strip back that hardened exterior jacket, you're going to reveal a 3 millimeter simplex cable inside this. It feels and looks much like a old style patch cord would. Okay, so it's still protected there, and they're typically riser rated, and you know, they're suitable for indoor facilities. Running that cable inside, as I mentioned before, if you had to go through the side of the house, you don't want the hardened drop cable inside the house. You would skin that back and just send in the 3 millimeter drop cable side of that type of drop cable. Number 3 is the connector. This is the SC connector, as you can see in the picture. This is the device that's going to plug into your micronode or your ONT at the customer premise. Connector 4, this is the hardened connector that plugs into the MST. Now again, relating back to the coax network, you know, when we'd put in drops, we'd always be cutting them to length, okay? Because field terminating MF connector is pretty straightforward. Field terminating a optical connector is less straightforward and a little bit more expensive. So, you know, we have been using fixed length optical drop cables for a long time, but if you think about that, if they're fixed length, almost in every case, we're going to need to store slack somewhere, okay? And I'll get to that in just a little bit, but that's definitely a consideration when whether you purchase a drop cable that's connectorized both ends, or it's connectorized one end, the hardened end, and then the customer premise end is left stubbed, so you can field terminate an SC connector. And then that gives you the advantage of not having any slack, and you can cut the cable to length to the side of the house. Okay. Next picture here is the types of drop cables and their lengths. A couple of the different options that our company offers is spooling them up. Of course, if they're greater than, I believe it's actually 300 feet. If they're greater than 300 foot, they're put on cardboard spools and makes it easier to pay out and install. If they're less than 300 foot, they're just going to be tie wrapped together. They're both offered, as I mentioned before, with single-ended dielectric and locatable types of cable. Some of the standard lengths on single-ended is anywhere from 75 foot to 2,000, double-ended 100 foot up to 350 foot. There are some other lengths. This cable or this slide is a little bit dated, but there's several different lengths. At least in my experience, cable drop lengths are typically 100 to 300 foot. Rarely will you get over, 500 foot. But again, depends on whether you're urban or whether you're rural. It's a little bit closer look at the actual hardened connector itself. The top two slides are what we refer to as an OptiTap connector. This is a connector that was designed and produced by Corning, and it's a good connector. And we probably, several years ago, developed our own, and we call that a DLX. And as you can see, the size of it is much smaller. It's almost half the size of the Corning style connector, but it offers our customers a couple of different options and a couple of different benefits we feel using the smaller connector. But they both do the same exact job, and they both seal very well. And this is what is referred to as a universal service drop cable. It's for low-rise MDU and some single-family unit applications. It takes the place of a standard outdoor drop cable. And the big advantage of it, like I was mentioning before, is that we can peel the jacket off to reveal that softer 3mm inner fiber cable. Now you can imagine when storing drop cable with a hardened jacket on it, that's the top picture is about the size you're going to be able to get to store that slack. You're not going to be able to coil it down much smaller. With smaller 3mm cable, as in the bottom picture, you can coil up a lot of that and store it in a very small location. So most commonly they're stored in the NID box. The slack is what I'm talking about, is stored inside the NID box in a customer premise. And if the system has been site surveyed and designed correctly, and the right length cable has been installed in there, you're seldom going to have any more than 50 foot of slack that you're going to have to deal with and store. If you think about it, there's only two places to store slack, and that's at the customer premise or back at the tap. And that hopefully segues into a slide that I have here just a little bit further down the road. I'll show you. Just wanted to show you a few pictures here of different installation examples that at least I've witnessed or been involved with. This first one here is what we call an FDH, Fiber Distribution Hub. This is a 144 fiber cabinet, and it's co-located with a V-hub, as you can see in the top picture. Right-hand side, there's a green cabinet. That's where the power supplies and the V-hub are located, and then there's conduit run underneath to the FDH, and that's where the fiber cable is managed in the optical splitters and everything. It's just that V-hub is basically driving that cabinet. Again, I mentioned before, 144, 288, 432, 864. Those are the fiber, the hub, or the cabinets, capacity on the distribution side.
Larry, looking at the FDH, is that integrally mounted on top of a vault? Because I've seen some vaults over the last 5 to 10 years where they're designed to have hardened structures on top of the vault, say a split vault, half of it's open, half of it's got mounting, or is this beside a vault?
No, it's a split vault.
Okay.
And the FDH mounts on the one side, the hole's pre-cut and everything. You simply bolt it to the top of that lid. Yeah. Okay. A couple more examples here, as I just showing. This is a 144 in the picture on the top with a 30 by 60 vault, and then this is a 288 below on the same size vault. So you can see there's not a huge size difference between one and the other. This is a pole mount FDH, kind of a unique niche market here. It's really good for regions that have a lot of snowfall. As you can imagine, if these are mounted on the sidewalk or next to a road or highway, they can become obscured once you get a few feet of snow. So locating them can be rather difficult sometimes. So that's why this company, at least from this picture, had chosen to pole mount them so they can have access to them year round. Again, and it's primarily used for overhead plant. Bad thing about this, of course, you're having a pole attachment. So what does that mean? You're going to have to pay somebody to do that for the privilege, okay? So that's the downside of putting it up on a pole. Splice closures, let's talk a little bit about those. As you can see here, I just got a couple of pictures I wanted to show you. Hopefully you can see in the vault that's directly below the FDH in the picture to the left are two splice cases, one for the feeder side, which is going to be low fiber cable count, anywhere from 12 to 24, and then on the distribution side, which is going to be that 144, 288. 432 or 864. Picture in the middle is how we manage the MST tails coming into that splice case. If you refer this picture back to one of those first few slides that I showed you with the designs, this is how we pull those tails into a splice case and seal them off against any water or air ingress into them.
And before you were saying the other end of the MST tail more than likely is a hardened connector to go into the device, right?
Into the residence, yes.
Yeah.
And I'm sorry, the slide to the right here, this is labeled incorrectly. This is not an MST. This is a splice closure. So sorry for that. I missed that. Overhead, aerial plant. This is how you can mount them. They'll typically come with a mounting bracket already, and then the MST snaps into that mounting bracket. So looking at the upper left-hand side, you can have strand mount brackets that are standoff in case you have a lot of cable on the strand, or you could tie wrap them directly to a strand, pole mount them, and then the pictures on the right are just of a couple of installations I've seen. Okay, let's talk about underground a little bit. I really like this product to the left. We don't produce it, but I think whoever made it's a really good idea. And this goes to that slack storage issue. They're called ped vaults, and it's basically a small pedestal with a small vault underneath it, and it allows you a nice little location right underneath the MST to store up all that slack of the, if you're using pre-terminated fiber cables, you're going to have to, manage that slack. So this is a good location to do that. Okay, so we've gone from the hub to the pedestal or the MST, and now we've got the drop cable coming in to the side of the house. So this is where we're going to mount a micronode, whatever it is. If it's an ONT or a micronode, don't really care. But this is the NID on the side of the house. We could also store our slack in this case. But to be honest, this location that I took this picture and the previous picture where the slack was stored in the vault, they're both the same exact location. So they didn't need to store any of the slack in here. Otherwise, you would have seen a coil of maybe 40 or 50 feet of this white 3mm cable inside this box as well, if they couldn't have stored it back out at the MST. At any rate, the cable comes in. This is the hardened drop cable coming in. At some point in here, I can't tell, they skinned it back to reveal the 3mm cable. And then that goes and swoops into the bottom of the micronode, which converts the optical signal to electrical, comes out on the coax, goes inside the house, hits its splitters, and is distributed throughout the home. Okay. Another thing. Go ahead.
A person on the call has asked, is this 900 micron fiber, the drop fiber?
Well, inside the 3mm jacket, it's 900 micron. And then you'll knock that off, and then you'll reveal the 250 micron, and then that's where you start preparing your fiber cable to connectorize it, if you will. But yeah, there is a 900 micron coating or jacketing inside that 3mm. Now, one of the things this picture, is not showing is an AC outlet. You can see there's a little wall wart down here getting ready to be plugged in. That was not installed yet. This is a brand new development, so different trades were coming in at different times, unfortunately, which happens a lot. So there will be a duplex outlet inside this box as well, just at a later date. Okay, so that was single family unit. I hope that gave you a little better idea where these things are placed in the network and what they look like when you actually get out there.
Larry, before you go to the MDU, so cable and conduit, even for drop, has been around quite a long time. Are you seeing anyone that has been kind of thinking ahead to what happens when people are digging in the rights of way and then these drops get cut? Are you seeing anyone that is saying we're going to put a 3/4 inch pipe from where the MST is located to the home, so if there's damage or something, we can pull a whole new one back in and avoid having to rebury something?
Yeah, so you're talking about direct bury a drop or a drop in the conduit?
Correct. Are you seeing
okay.
anybody doing drops in the conduit to the side of the house?
Yes. Obviously, it's more expensive to do. Your direct bury is always going to be your cheaper option. But again, it depends on where you are. Out west, if you consider California, places like that, there's a lot more rock in the soil, and it's much more difficult to trench. And, that is a problem in itself, but it also affects the longevity of even a direct bury cable, is what I've been told. That type of ground environment is really hard on the cable, and so essentially in the Southwest, they've been putting in conduit. Okay, I know it's cost a lot more, but they figure over the long term it's going to save a lot more in service calls for drops that have broken or deteriorated or whatever. But it kind of essentially it breaks down to the type of terrain that you're going through. If it's nice soft clay soil like in the Midwest or whatever, it'll always be direct buried. Did that answer your question?
Yeah, I think that's good.
Okay, all right. Well, let's look at MDUs real quick here. I know that I'm going a little bit long. Hopefully everybody's able to join on here. We'll probably conclude in about another 10 or 15 minutes or so. I want to talk about indoor MDUs. They're the types of equipment that fit in there, and this is again just a 30,000-foot view of a typical MDU. But we're going to have our fiber distribution cabinet in the basement or the ground level. And then on each floor above it, in the riser closet, most typically, not always, but most of the time, we're going to have a fiber distribution terminal. From that terminal, we're going to run our drop cables to the individual residences. Okay. If we looked at this is a splice design. So we have the fiber distribution hub or cabinet in the basement, and then we have preterm stubs coming down from these FDTs or fiber distribution terminals. This is a 24 fiber, this is a 48. Those are all coming down with their own cables and being spliced into the fiber distribution cabinet. Look at a garden style or a low rise. This is just again a totally different type of MDU, but again several different buildings in the same general area. And with this type of design, you're going to probably not have an indoor mounted fiber distribution cabinet. You're going to have an outdoor mounted fiber distribution cabinet that serves all of these buildings. Okay, so if you see on the grayed out box that I have on the right hand side, the next slide, I'm going to drill into that area and flip it vertically so you can see again, like we were talking about in the single family unit example, of what this equipment looks like and where it's placed in the outside plant. So we have our V-hub, which is feeding the optical signal from the head end. The V-hub is going to give us several different fiber outputs, which is going to drive the fiber distribution hub. In this case, the two distribution outputs are in cyan color. One exits out and goes up the road to a splice closure. From that splice closure, we're going to have a MST tail. And I apologize for the legend here and the description of the MSTs. Everything is a bow tie. That was the design firm that built this, so I wouldn't have used those types of icons, but it is what it is. So this is the MST right here, and then this is the micronode at the individual residence in the building. Okay. Drop cables are in blue again, going to each of the individual residences. These distribution terminals could be on the ground floor, if it's a I don't know, 1, 2, or 3 floor building. If it's multiple stories, they will be distributed equally amongst the floors. And we talked about outdoor fiber distribution cabinets quite a bit earlier. All I'm going to say is that there's an indoor equivalent of that. Okay, looks exactly like the outdoor. The functionality, the fit, and everything is the same, except it's not hardened against the outside environments. As you can see, where my pointer is here along the top-hand side, those are all ports where all of those distribution terminal cables are going to come down from the respective floors and come in and terminate into this box. Okay, again, for MDUs, because you're fairly dense, it's a centralized splitter design, pretty typical. Okay. And again, the sizes, typically that's when you do design, you need to size the fiber distribution cabinet for the size of the building that you're designing. Just a couple of examples here. This is two indoor fiber distribution cabinets. So one is a 72 fiber value and the other is a 144. The one on the 72, this is a connectorizer, what we refer to as a rapid installation. Okay, so each one of those fiber distribution terminals is going to come down from the respective floors and simply plug right into this with a MPO connector. The version below is more traditional and it's spliced on the distribution, the distribution side and the feeder side for that fact. This is a fiber distribution terminal. This is the device that mounts up in the riser closet and all of the drop cables are connected to. And again, 6, 12, 24, 48, 72, all the way up to 96 fibers. This is a rapid distribution terminal, and these have been around for quite a while. What it does is reduces your installation time, essentially. You mount this on the side of the wall. You take the white, excuse me, or the yellow cable, as you can see on the reel, in this entire box in that spool spins around on the wall while you're pulling the cable down the vertical risers. Once you get it down to the fiber distribution cabinet, you just plug in this MPO connector and you're essentially done doing that floor. This is a mini version of the previous slide. This is the previous slide, those are 12 and 24 fiber versions. This one is 4, 8, and 12 fiber version. Okay, so a much smaller building, smaller deployments. It's still built out the same way and still has the cable inside the device, which you pay out by pulling down through the riser cables and then plugging into the FDH. Drop cable indoors does not have to be hardened, obviously, and so this is the type of cable that you're going to use. It's typically a 3 or a 5 millimeter cable jacket construction. They almost always use RBR, or reduced bend radius cable, which reduces the risk to insertion losses created by staples or wrapping hard around a corner, things of that nature. So it's pretty robust cable. Most generally, when you purchase it, you're going to do it one of two ways. You're going to order it single-ended, which is the picture on the right-hand side, and then, of course, a reel of single-ended cable on the outside, on the bottom. The other end is just a stub end, okay? And you're going to field terminate that, but at least with this drop cable, you have one end that's factory terminated. Couple of different ways of doing this, of pulling the drop cable, and again, we're talking only greenfield because we're going to have microduct more than likely in this building, is we're going to take that reel of single-ended cable and bring it to the customer premise, and then we're going to pull or blow it through the microduct to the riser closet. Once it gets to the riser closet, we're going to cut it to length, we're going to field terminate a connector onto the end, and then plug it into the distribution terminal. That'll complete our circuit back to the fiber distribution cabinet. Another way is to use bulk cable where we're not terminating one end of it. We're going to take that reel of cable up to the customer prem, blow or pull it through the microduct, terminate both ends. A little bit more work here. That's why the single-ended is kind of a nice option. And I always prefer to have that in the customer premise. Like I say, if there's any field issues terminating that little connector that takes them offline, at least you're probably only going to be dealing in the closet and you won't have to go to the customer prem to replace the connector, if that's the issue. Micronodes, these are just the devices that would fit inside that NID box on the side of the house. And then I just wanted to show you a few pictures of MDU examples, ones that I've been involved in. I think, looking at the block diagrams that we have in the previous slides and as well as the stick drawings and everything, that's all good and that helps explain it to you logically in your mind, but seeing the actual pictures I think are of value as well. So just wanted to show you a few of these. We're just about done. I've probably got maybe 4 or 5 of these slides and then that's it. This was a high-rise in Chicago, brand new building. You might be able to see that from how clean it is in the basement of this building. But this is a fiber distribution cabinet that's 288. Off to the left of this, mounted on that plywood board, is the V-hub. And this is what's providing the signal input to the splitters in the fiber distribution cabinet. The picture to the right shows the front subscriber access panel, and I believe it looks like maybe 1 by 32 optical splitters have been plugged in up top, and their pigtails routed down. It looks like they're in the process of identifying the subscribers and terminating the outputs of those splitters. This is a riser closet with a 24-port terminal, this is a rapid terminal that's a 24-port, this is a 12-port. In this building, I can only guess that they needed 28, so what they did is they used 24 in this, and then 4 out of this guy. You can see this here, and that begs the question, what's going on? Remember what I was talking about pre-terminated cables? You need to manage the slack. So this is how this contractor decided to manage the slack, which I think is good. But, again, this is where the advantage of a field terminated connector comes into play, where you can cut the connector and cut the cable to length, and you don't have to manage this over-length slack. They did a nice, clean job of it. It's just that it's additional work. And as we progress with different ways of terminating optical connectors in the field, it becomes much more commonplace, and it's not as specialized, and it's not as expensive. So this slack issue is probably going to go away in the near term. This is just a shot of a through closet where we have the pipe coming from the floor above it to the floor below it, and all the different cables running through. Just wanted to show how you can identify. These are the, I'll call them tails. In this case, it's the same thing as an MST, but it's a box, up on the riser closet. These are the fiber tails from all of the fiber distribution terminals from all the floors above the floor that we're on now. Gray cable is just some existing telco twisted pair. And then you can see also this building was pulled for a traditional coaxial distribution as well, so that's still in there. I'm not quite sure why, but that was still there. And here's our riser closet with the individual conduits. You can see the addresses of the individual residences written on the conduits. And then if you recall from a couple slides prior to that, this black cable is the drop cable. So this is if you followed this up, that would go to the prior slide with the loop of slack cable. So this is our drop cable going down to our customer premise. This is the customer premise. Picture in the upper right-hand corner is the media box. This is typically mounted in a laundry room or in a closet or something of that nature. It's just a general between-the-joist Hoffman-type closure. It has to have AC in it to power the device, so you can see the duplex outlet right here. Okay. Then the optical signal, a little bit of more slack on this end of that drop cable, and then plugging into the micronode. This installation is not yet complete, so there will be a coax cable here to power the device, and then the other one with the RF output, which is in more cases than not, it's going to drive several outputs in the residence itself. You can see on this coax cable right here, it's all the drops to all the different locations and wall plates have been identified with living room, bedroom, etc. And then the picture down the lower right-hand corner, that's the finished product, and that's about all the customer sees or knows about a fiber to the home network into their residence. It's still going to look like a coaxial, cable termination plate there on the wall. They don't see everything that we talked about going on before that gets to that point. So that's about all they see. And that concludes my presentation. I'd be happy to try and field any questions you guys might have. Hopefully I'll have an answer. If I don't, I can promise you I will get back to you and provide you one if possible. And Bill, I'll turn it back to you. And if we do have any questions, I'll try to field those.
So, Chris, as you look at this, and as we've talked for years about just MDU wiring and such, labeling, toning out wires has always been an ongoing struggle to get things right. Has any labeling kind of come to the, stepped into the future a little bit? Are there better labeling examples now for when we're connected onto these fibers? Do we have better labels, better systems, barcoding, anything like that?
Well, yes and no. I'll step back with regard to the fiber distribution cabinet and if you remember the plug-and-play splitters with the 2-meter pigtails coming out. Those are all barcoded and identified both with a barcode and a number. So those are easy to identify. When you get out to the drop cables, the quick answer is no. The better answer to that is that at the fiber distribution terminal, at least with my company's products, we put what's called a designation card inside the device. It usually fits on the door that you open up, and it gives you an opportunity to write down what port is connected to what residence, whether it's an address or an apartment number or a building number or whatever the case may be. It gives you a physical place to write down where that drop is connected to. And then you can obviously go identify each of the fiber ports on the device are labeled, 1 through 12 or 24 or whatever. So not unless the installer puts a Budco tag or something on the actual drop cable when they're putting it in. Those are the only means that I know of to properly identify drop cable.
Okay. Well, I'm just waiting. We've had quite a few questions from the groups across the state, and just waiting if there's any other questions. Any other words of wisdom? Things that you've seen so far that you were kind of surprised by when you were out, because you've made site visits, you've been involved in this.
Yeah, I would say probably just study the area that you're planning on putting fiber to the home in. As I said, there's different types of architectures that serve those best, and if you choose one that's has a little too many bells and whistles for an area that doesn't need it, it's going to cost you a lot, and you're not going to make up or I'd say not make up, but it's going to take you much longer to get your return on investment in that network. And I guess what I'm saying is you wouldn't put a centralized architecture out in a very rural area. So pay attention to the serving area, how many homes pass per mile. That's going to direct you towards the best design to use to serve that area.
All right. Something you didn't touch on before. We've obviously, as an industry, have been using muxing for quite some time. CWDM, DWDM. With the 32 fibers going to the units, are they of different wavelengths and then are muxed back at the central location? How is that happening?
Yeah, that's a really good question, and maybe I should touch on that. I just don't think of that, But yeah, you're only going to use the 2 wavelengths that we use for RFOG or for PON. And that's going to be on the individual cable that feeds that splitter. The splitters are equal. It's a wideband splitter, so everybody gets the same exact signal off of that splitter, just at a reduced power level.
Right. And then they don't all talk at the same time, correct? If we think of talking, it's time division multiplexed, isn't it?
Well, no, I mean, like I said, and we should probably concern ourselves with the future more than the past, but yeah, in the past for data and phone and things like that, it would be time division multiplexed. Now, give it 5 years or 10 years, everything's going to be IP based, whether it's video, whether it's, of course, video on demand, whether it's telephone, any type of service going to a customer is going to be IP based. So in the end, it's going to use, what do they call it, CSMDA or carrier sense multiple collision
Yep.
avoidance.
Yep.
That's what's going to be used to manage the system. It listens before it transmits, essentially.
So the micro nodes are transmitting essentially in the area. They're all transmitting on the same wavelength back. So it's really not a muxed solution, correct? It's one wave down
correct.
and one wave.
Yep.
Right.
Exactly.
And then when you look at those micro nodes today, inside Charter, inside several companies, they've got very robust node health scoring. We want to have the right levels in the home. And typically, I can think back to the early 90s when we started the latest round of upgrades. We were thinking 2 outlets in the home and so on. And now we've got devices like unity gain amplifiers with 10 ports on them, an 8-way splitter, a port for power, and another port for, say, a dedicated modem or MTA. What kind of levels are we talking coming out of these micro nodes?
Well, that's a little hard for me to answer because, like I said, we're kind of on the passive side of the network. But as memory serves, 0 to -3 dBm comes to mind. You generally have like depending on, again, whether it's RFOG or PON, 23 to 26 dB link budget from the head end out to the customer.
So
32 ways going to chew up. Go ahead.
No, that's on the light side. Are you aware of what kind of operating RF output they have on the other side?
Oh, sorry. Yeah, they're usually 10 to 17 dBmV.
Wow. Okay.
So, and that's, again, you brought up the point. In the past, 20 years ago, you had maybe 2 TVs in a house. Today, it's not uncommon to have 5 or 8. So you're going to have to drive an 8-way splitter. There's 12 dB loss. That's why we would offer a 17 dB gain, micronode.
Right.
But I've seen anywhere from like 10 to 17 dBmV is probably pretty typical.
Right. And the neat thing about this is you don't have to necessarily do a lot of cable engineering going back into the network to make sure that your return levels on your devices are okay, because you're at the home. The micronode is at the home.
Exactly.
Okay.
Yeah, you're only going, in most cases, probably 100 feet or less, so there's no need for that. And again, that's kind of the beauty. That's kind of the beauty of these, optical passive networks. Is as long as the network is designed correctly, and all the losses have been accounted for, there's no need to measure anything other than just a sanity check. Everything should just end up sitting just about where it should be. Now, that's kind of a broad statement, but in general, that's really the truth of it.
Right. Back in the day when we were doing whole home checks, the original specs, some of the modems and devices, they actually liked a little bit less signal than more. And of course, you were running digital carriers down lower than analog carriers. It'll be interesting to see how that kind of evolves once you've got a fixed higher level coming from these micronodes to the same devices in the home.
Sure. Good point.
Yep.
Understand.
Well, folks, any other questions? We've had a slew of them. Chris has answered them all. All right, Chris. Well, then I want to say thank you very much. One of your partners in crime, Kitty Corcoran, was making sure that we had talked early, and I told her, don't tell Chris, but excellent presenter. Thank you very much. Love the slides on what it showed as we see it out in the field, because most of our people who are on this webinar, they deal with in the home, in the field every day. They know what they deal with. They know that they've got depth issues, just bearing stuff to homes, call for locates, that sort of thing. So let me ask you maybe the last question. The fiber cabling itself, it's always easy to locate our drop cable because of the shielding. Is there any metal shielding or anything else that will allow the locating companies to find this cable? Fiber cable drop.
The drop cable, yeah, sure. I mentioned before in the slide about the drop cables that at least CommScope offers a dielectric type of drop cable with no metallic component, and then we have a locatable drop cable with a metallic sidecar, if you will, jacket that runs alongside of the flat drop cable in the same jacket. So you are able to identify it. And when the cable's installed at the residence or at the tap, usually just leave about 6 inches of that out so you can clip on and then go tone the cable.
Yep. Okay.
Yeah.
Very good.
Great. And tell Kitty thank you. She's always keeping me honest. Keeping me.
Well, she's one of those. She's a fellow Northern New Yorker. So we appreciate the time we get together too. So Chris, thank you very much, and folks, thank you for being a part of our webinar, Fiber to the Home, and thank you again, Chris Bright from CommScope. Wonderful.
Thanks very much, Bill, and again, thanks to the Buckeye State Chapter for inviting CommScope to do this presentation. We also appreciate the opportunity to get in front of our customers and show what our products can do and the things that we have available to support their business. And
thanks to the SCTE for allowing us to use the webinar and getting this all put together. Folks who are on the call, we are recording this, and as we work out at our local chapter how to get links and publish those for these recordings, we're going to get them up so you can come back and play back through it. So thank you.
Sounds great. Thanks, everybody.
Thanks. All right. Bye-bye.
Adios.